Welcome to Module 8, Network Layer. This is where IP addressing gets its full formal treatment, packet headers, IPv4 versus IPv6, and how both hosts and routers make forwarding decisions. Everything from Module 3's addressing concepts becomes concrete here. Objective: explain how routers use network layer protocols and services for end-to-end connectivity. Preview the topic table on screen. Network layer characteristics, the IPv4 packet, the IPv6 packet, host routing, and router routing tables. This is a long module, covering both packet structure and the actual forwarding logic. The network layer, Layer 3, lets end devices exchange data across networks. IPv4 and IPv6 are the main protocols, alongside routing protocols like OSPF and messaging protocols like ICMP. Walk the four-step flow on screen, addressing end devices, encapsulation, routing hop-by-hop, and de-encapsulation at the destination. IP encapsulation wraps a transport layer segment with an IP header to form the IP packet, shown on screen as segment header plus data, becoming IP header plus segment header plus data. This layered approach lets each layer develop independently. A transport segment can be packaged by IPv4, IPv6, or any future protocol without changing anything above or below it. IP was deliberately designed low overhead. It does only what's necessary to deliver a packet. 3 defining characteristics shown on screen: connectionless, no handshake before sending; best effort, delivery isn't guaranteed; and media independent, works over any physical medium. These 3 get their own deep dive slides next. IP is connectionless. No dedicated connection gets established before sending data, similar to mailing a letter without calling ahead. The sender has no way to know in advance if the destination is even present or ready. The packet just gets sent. This is a deliberate design trade-off, not a flaw. It keeps IP simple and fast. Being connectionless means no extra header fields are needed to maintain a connection state, which keeps overhead low. But the trade-off is real. The sender doesn't know if the destination received the packet, or even if it could read it. IP doesn't guarantee delivery. Some packets may simply be lost, with reliability left to upper layer protocols like TCP. Unreliable specifically means IP can't manage or recover corrupted or lost packets on its own. No built-in retransmission. That's TCP's job. Separately, IP is media independent. The exact same packet can travel as electrical signals over copper, light pulses over fiber, or radio waves wirelessly, with zero change to the packet itself. The IPv4 header, shown on screen, a variable length header, minimum 20 bytes, up to 60 with options. Walk through the field layout, row by row, version/IHL, type of service, total length on row 1, identification/flags, fragment offset on row 2, TTL/protocol, header checksum on row 3. Then, source and destination IP addresses. Read every header diagram left to right, top to bottom. That convention holds throughout networking. Key IPv4 fields explained. Version IHL identifies the IP version and header length. TTL limits packet lifetime, decremented by 1 per hop, discarded, and ICMP notified at 0. Protocol identifies what's next. ICMP equals 1, TCP equals 6, UDP equals 17. Header checksum catches header corruption. Source destination IP are the 2 most referenced fields and usually stay unchanged in transit. Identification/fragment offset handle reassembly if a router had to fragment the packet. IPv4 has 3 major limitations. IPv6 was built to fix, shown on screen. Address depletion. Only about 4 billion addresses can't keep up with device growth. Lack of end-to-end connectivity. NAT lets multiple devices share one public address but hides internal hosts, breaking some technologies. And increased complexity. NAT was only ever meant as a stopgap. It adds latency and complicates troubleshooting. IPv6 development began in the early 1990s, when IETF saw IPv4's limitations coming. 3 big improvements, shown on screen. Increased address space, 128-bit hierarchical addressing versus IPv4's 32-bit. Improved packet handling, a simplified header with fewer fields, and eliminating NAT's need entirely. The scale comparison is staggering. IPv4's approximately 4.3 billion addresses versus IPv6's 340 undecillion. IPv6's biggest improvement is header simplification. Fixed 40 bytes versus IPv4's variable 20 to 60, with fewer fields for more efficient router processing. Walk the field table. Version: 4 bits, always 0110. Traffic class, like IPv4's DS field. Flow label, packets sharing this get consistent handling. Payload length, next header, equivalent to IPv4's protocol field. Hop limit replaces TTL, and the 2 128-bit source destination addresses. Every packet originates at a source host, which uses its own routing table to decide where to send it. 3 destination types, shown on screen. Itself, the loopback interface, 127.0.0.1 or 1, tests the host's own TCP/IP stack. A local host shares the same network address, or a remote host, different network address entirely. The default gateway, usually a router or layer 3 switch, is what routes traffic to other networks. Use the room and doorway analogy. To reach another room, network, you first need to find the doorway. A default gateway has an IP in the same range as other local hosts. Critical point: no default gateway configured, or it being down, means traffic simply cannot leave the local network. A host routing table typically includes a default gateway entry, learned via DHCP or manual config for IPv4, or via router advertisement or manual config for IPv6. Walk the example on screen. PC1 and PC2 both point to 192.168.10.1 R1 as their gateway. Any traffic bound for a remote network goes there by default. This creates a default route right in the host's own routing table. On Windows, RoutePrint or netstat-r both display the same host routing table, destination networks, the gateway to reach them, and the local interface involved. Worth emphasizing: every host, not just routers, maintains its own routing table to decide where outbound packets go. This is a good moment for a live demo if you have a Windows machine handy. Routers keep routing tables too. When a packet arrives on a router interface, walk the 3-step process shown on screen. The packet arrives and gets de-encapsulated. Layer 2 header/trailer stripped. The router searches its table for the best/longest matching entry, then re-encapsulates with a new Layer 2 header/trailer and forwards to the next hop. A router's routing table holds 3 entry types, shown in the table with R1's actual examples. Directly connected: an active interface with an IP configured, e.g. 192.168.10.0/24. Remote network, learned via static config or a dynamic protocol, e.g. 10.1.1.0/24. And default route, the gateway of last resort when nothing else matches, 0.0.0.0.0/0. Static routes are manually typed in by an administrator. 3 characteristics shown on screen. Manually configured, exact entry typed by hand, doesn't self-adjust. A topology change means manual reconfiguration, and best for small networks, few or no redundant links. The diagram shows a static route to 10.1.1.0/24 via R2. If that link fails, traffic doesn't automatically reroute through R3, even though a path exists. Dynamic routing protocols like OSPF or EIGRP let routers automatically learn about remote networks, including default routes from each other, adjusting on their own when topology changes. Example on screen: R1 and R2 exchange OSPF updates, each telling the other about its own connected network. Configuration is minimal. Just enable the protocol on directly connected networks, and it handles discovery, path selection, and failover automatically. Some networks blend static and dynamic routing together. The show IP route command displays a router's actual IPv4 routing table. Each entry starts with a code showing how it was learned. Walk the table on screen. L. Local interface IP. C. Directly connected network. S. Static route. O. Learned via OSPF. D. Learned via EIGRP. Then walk the live example output line by line, matching each code to what it means. Close the module walking each bullet. The network layer's 4 operations: addressing, encapsulation, routing, de-encapsulation. IP's connectionless/best effort, media-independent nature. IPv4's variable header versus IPv6's fixed 40-byte header and 128-bit addressing solving exhaustion. Every host's own routing table and dependence on a default gateway, the 3 router routing table entry types, and static versus dynamic routing trade-offs.